Okay, so can anybody confirm to me that what they are seeing on my desktop right now?
Sir, we are seeing the slide lecture 3, chapter 10, vapor
Okay,
cycle, power
okay,
cycles.
okay, okay. Okay, so coming towards our today lecture, which is lecture number 3. Again, this is from your chapter number 10. Previously, we looked for vapor power cycle, which is the ideal one. Okay, so we already know that how to thermodynamically analyze the ideal vapor power cycle or Rankine cycle. In this case, we are looking for the actual one. Okay, so we will see that how your actual vapor power cycle looks like and how to deal with the actual vapor power plant. Okay, so coming towards the actual vapor power cycle. Okay, so the main difference between the actual and the ideal one is the availability of irreversibilities in your actual vapor power cycle, which deviates your from the ideal vapor cycle. So where these irreversibilities come from? So we already know that when we are analyzing the ideal case, we have to assume that the system is reversible and there is no irreversibilities in the system. But when there will be irreversibilities, so then there will be, it may be causes the cause of these irreversibilities are fluid friction. Okay, so the fluid friction causes the pressure drop in the boiler, in the condenser, and the piping between various components. So as a result, steam leaves the boiler at somewhat lower pressure, and in addition, the pressure available at the inlet of the turbine is lower than the pressure at the exit of the boiler due to the losses in the pipe. And pressure drop in the condenser is usually small, and the larger pump is required to pump the fluid to higher temperature than those required in the ideal to compensate these pressure drop. So these are the some sources from which the irreversibilities come from, because we already know whenever we have to deal with the actual system there will be a friction. Okay, and that friction will come from the fluid friction or any type of other losses which are associated with your pipe flows. Okay, so then there will be a heat loss. Okay, so heat loss occur from the steam to the surrounding. Okay, definitely if there will be a heat transfer, there will be a losses in the surrounding. Okay, for the actual system through various components. To maintain the same level of network output, more heat needed to be transferred to the steam in the boiler to compensate these undesirable desired heat losses. As a result, cycle efficiency decreases. So your actual vapor power cycle, the efficiency will be less, okay, as comparison to the ideal one. Okay, so coming towards our TS diagram for the actual one. Okay, so previously we already know that whenever we have to go for the ideal one, the ideal case. Okay, I will just draw in the blue line. Okay, so for the actual one, if you notice that this one, this two, so this is your actual one. Okay, the continuous line. Okay, so actual vapor power cycle looks like this. Okay, we already see in previous lectures. Okay, but whenever we are dealing with the uh, okay, so this is your ideal Rankine cycle, which I highlighted in the blue one. So your actual vapor power cycle, there will be a deviation from 1 to 2. Okay, so there will be an increase in isentropy. uh, okay, there will be an increase in entropy value, because if you see that this is an increase in entropy. So this point, which is previously at 2, just shifted to towards your right side. Okay, then there will be a pressure loss, pressure drop in the boiler. Okay, so this point, which is the continuous line, will be shifted from this to this dotted area. Okay, so this dotted area become your pressure drop. Okay, so because there will be a decrease in pressure in the boiler, then there will be irreversibility in turbine as well. So again there will be an increase in entropy value. So your point, which is previously at this state, okay, in the ideal case, right now this shifted towards your 4 dash, so you can call it 4 dash. Okay, so this is due to the irreversibility in turbine, and that increase in isentropy, increase in entropy will always to be seen on the exit of your turbine or exit of your pump. Okay, so that's why the point 3 is not changed in all the cases of your ideal, or either it will be an actual one. So then there will be again pressure drop in the boiler. So again this point will be shifted towards your dotted one. Okay, so there will be a pressure drop in the condenser as well. Okay, so now coming towards our more elaborated TS diagram. So again in this case, okay, so this is point 1, this is 2. So 1 to 2s is your isentropic process, which is from your ideal Rankine cycle, and 1 to 2a is your actual Rankine cycle. Okay, so this will be for your actual one. Okay, so then 2 to 3 there will be a heat addition. Okay, so Q in. Okay, so then there will be a 3 to 4s is your isentropic work for your turbine. Okay, and work for your turbine, and then for 3 dash to 4a is your actual work. Okay, so now coming towards that, previously it was easy that we just have to find the enthalpy value of 1, 2s, because that will be isentropic process. So if the state number 1 is known to us, we can easily find to 2s or isentropic state at 2 1 also. But in this case, this point is deviated from increase in entropy towards your right. So then we will see how to find the enthalpy value for these states as well. Okay, so now coming towards our. Okay, so this we already talked about that there will be a two causes, which is your fluid friction or heat losses to surrounding are the two common sources of your irreversibilities in your actual turbine, actual vapor power cycle. Okay, so now coming towards whenever there will be an involvement of irreversibilities, so these irreversibilities are to be seen on your pump, okay, where you are supplying some sort of work, and in your turbine as well. So whenever these things are involved, so you have to define some efficiency of your pump in term of your isentropic work. Okay, so you already know that we have to divide your isentropic work over actual work. Okay, so this term will be, because in the case of your uh, pump, because this is a pump one. Okay, so ws is lower. Okay, because in your when there will be isentropic process, it's mean you have to supply minimum work to your pump. Okay, but when there will be actual work, okay, so in the actual work, because of your irreversibility, you have to supply maximum work to your pump. So the above term is lower, and the down term, which is in your denominator, is your maximum one. Okay, so h2s, again you already know that the work is defined as your enthalpy at your exit minus enthalpy at your inlet. Okay, so h2s, this is I am talking about the isentropic one, h2s minus h1. Okay, and then actual work, so one is your exit, one is your inlet, and 2a is your exit. Okay, so h2a minus h1, so here this term uh, will be defined. Okay, so for so in order to find out the isentropic efficiency of your pump, you need h2s value, h1 value, h2a, and h1. You can easily find the value of your efficiency of your pump, isentropic efficiency of the pump. Similar case for your turbine as well. Okay, so the difference between the turbine and your pump statement is, in this case, wa is in your above and ws is in denominator. Okay, so why this will happen in this case? Okay, so again, in this case, the work which is your actual one, which is your turbine work, okay, in the isentropic case it will be minimum. Okay, and in the actual case it will be minimum, and in the isentropic one it will be a maximum, because you are gaining maximum power output from your turbine. So mean your above term will be minimum, and this one is your maximum term. So in order to define the work done in the form of enthalpies, again you have to know from your energy analysis in the previous lecture that h3 minus h4a. Okay, so this term will be defined for actual one, and then h3 minus h4 is your in isentropic one, work done for your isentropic turbine. Okay, so this is how we can define the isentropic efficiency of your pump and turbine for your actual vapor power cycle. So we will practice one question as well. So then you can, I think, easily understand how to apply these equation on your vapor power cycle, which is working on the actual one. Okay, so now coming towards the question. Okay, so consider first read it. Read the question. So consider a 210 megawatt steam power plant that operates on a non-ideal Rankine cycle. So in this way, we can find that this is defined at non-ideal. So it's mean this is the actual vapor power cycle. Steam enters a turbine 10 megapascal and 500 degrees Celsius. So it's mean your point number three, okay, is known to you. That is pressure is 10 megapascal and temperature is 500 degrees Celsius and is cooled in the condenser at a pressure of 10 kilopascal. It's mean your this pressure is known to you, that is 10 kilopascal. Assuming an isentropic efficiency of 85% for both turbine and the pump. Again, so here the isentropic efficiency of the pump is given to you and isentropic efficiency of turbine is also given to you because it is mentioned is same. So both are 85%. Okay, so it is mentioned in the question. Show the cycle on the TS diagram. It is already shown over there. And determine the quality of the steam at the turbine exit and the thermal efficiency of the cycle and mass flow rate of the steam. Okay, so now we will see that how we can solve it. Okay, so starting from the state one, we already know that the pressure is 10 kilopascal. So we can just go to thermodynamics table. I hope all of you know that how to find these values by using thermodynamics table. I'm not going to repeat it again. This will from your saturated liquid one. Okay, so W pumping. Okay, so the difference between the previous question which you already solved is that here you have to find the actual work for your pump. Okay, previously you have to find the isentropic work for your pump. Okay, so here the equation is the same, specific volume into P2 minus P1, but here the difference is that you have to divide the isentropic efficiency of your pump. Okay, by your by this value. Okay, so this value come from this specific value come from your state one. Okay, this is given in your question, this is again given in your question, and this is also given in your question. So by just putting all the value you can find the actual work. Okay, so this is your actual work for your pump. Okay, so previously we are finding the isentropic work. Okay, so now we have to find the actual enthalpy which is at state number. So we just describe because this is 2s and this is 2a. Okay, so you can just define that this is 2a h2a. So h2a is equal to h1 plus actual pump work. Okay, so this is already given from your state one. This you already find out in the previous state, and now you just plug in all the value, you will get the actual enthalpy at h2a. Okay, so in this way you have to find the actual enthalpy for the state number 2. Coming towards state number 3, which is your superheated region. Okay, so for superheated region, pressure and temperature is already mentioned in the question. Okay, so just read the pressure and temperature and go to thermodynamic table for the superheated one. Okay, superheated water, and you can easily find the enthalpies value and entropy value for this case. Okay, so now coming towards state number 4. Okay, so these are all the approaches which we already use in the previous lecture as well. So H4S, you already know the pressure is 10 kilopascal. It is an isentropic process. So S4S is equal to S3. So S3 is already defined. So you can easily find the quality at that point as well. Okay. So again, you can also find the enthalpy for the isentropic enthalpy for 4 point. So HF is already given in your thermodynamic table. You have to find it out. X4 is mentioned over there. So you have already find out in the previous state. FG is also given to you. Okay, so just plug in all the value 2089.7 kilojoule per kg. Okay, so now coming toward H4A. Okay, so how to find this? Because we all have to find both 4A and 4S. Okay, so 4A we have to find out from the isentropic efficiency of the turbine. So isentropic efficiency of the turbine is given to you by the previous relation H3 minus H4, which is your actual one. Okay, so we have to find this actual H4A, H3 minus H4S. Okay, so H4A we have to find, H3 we already find previously. Okay, this is given in your question. H3 is given to you. You already find from previous state. H4S you have just find out in the previous condition for the 4s isentropic one. Okay, so now all values are given to you. Just plug in all the value, you will get the actual enthalpy value for your state number 4. Okay, so now coming towards your quality. Okay, so for the quality again you have to use for the state number 4, but here you have to use the actual enthalpy value. Okay, so again use this H4 which is your actual one. HF you can easily find out from your 10 kilopascal range. HFG is also given from your 10 kilopascal from your pressure table. Okay, so you can find the quality of your steam here. Okay, so now coming towards the efficiency, we already know we need Q in, Q out. Okay, so for Q in, H3 minus H2. Okay, so here H2, previously when we are dealing with the ideal one, we have to use H2S. Okay, which is your isentropic enthalpy. Here we have to use H2A, which is the actual enthalpy value. So keep it remember that you have to use the H2A value here when we are dealing with the actual vapor power cycle. Okay, so here just plug in all the value because this already have to define from the previous states. Q
सर एक
out
बात बताइए,
G.
सर ये एंथैल्पी पी और एंथैल्पी टी की वैल्यू डिफरेंट आएगी या सेम होगी?
किस पॉइंट की बात करें आप?
सर किसी भी पॉइंट के ऊपर, मतलब ये जो एन टी है या एन पी है, इन दोनों की वैल्यू में फर्क होगा?
नहीं, एन टी नहीं है, ये एफिशिएंसी है ना आपकी,
जी जी,
एफिशिएंसी आइसेंट्रोपिक।
एफिशिएंसी पी और एफिशिएंसी एट पी, तो ये पी और टी वाले में, दोनों में, इन दोनों एफिशिएंसीज में क्या फर्क है?
इन दोनों एफिशिएंसी में फर्क ये है कि ये हमने क्वेश्चन में डिफाइन कर दिया है कि आइसेंट्रोपिक एफिशिएंसी ऑफ टरबाइन इतनी है, आइसेंट्रोपिक एफिशिएंसी ऑफ द पंप इतनी है 80% फॉर एग्जांपल। लेकिन अगर फॉर एग्जांपल क्वेश्चन में गिवन है कि आइसेंट्रोपिक एफिशिएंसी ऑफ द टरबाइन इज नॉट इक्वल टू आइसेंट्रोपिक एफिशिएंसी ऑफ द पंप, सो इट्स मीन you must have to find the value which is the isentropic efficiency of the pump is different from your isentropic efficiency of the turbine. In this question it is mentioned it is same, so we have to deal with the same value.
ठीक हो गया।
Okay, so in the coming question you will see that because most of the time it will not be the same one. Okay, so here we are just assuming that these are the same thing. Okay, so now coming towards W net. Okay, so Q in and Q out. Okay, Q out first we have to deal with. So again here you have to put the H4 actual value, okay, which we already defined in your previous case. Okay, so again this is your H1 which is coming from the state 1. Plug in all the value, you can find out the Q out also. Okay, so now we need W net, which is your W for your cycle. Okay, so again put all the value and then you can find the W net as well. Okay, efficiency of the turbine, efficiency of your whole cycle is given by W net over Q in. Okay, so plug in all the value, you can easily find the efficiency as you have already done in your ideal case as well by using the same procedure. Again, you need a mass flow rate. Okay, so this is your power which is given in your question that it is a 210 megawatt power plant. Okay, and then W net you already find in your this area. Then you can easily find the mass flow rate as well. So this is how you can deal with your actual vapor power cycle by using your actual enthalpies and your isentropic enthalpies value. Okay, so now coming towards the next question. Okay, so this is example 10-2. Okay, so this is if you can read it. Okay, so a steam power plant operate on the cycle which is shown in figure 10-5, which is available in your book. If the isentropic efficiency here again the same thing which one student is asking before, that the isentropic efficiency of the turbine and the isentropic efficiency of the pump in this case is different. So we have to put two different values. Okay, previously we are just mentioning that it was same in the problem statement, so we have to use the same value. So in this case we have to use different values for each of the case. Okay, so first thing, the thermal efficiency of the cycle, again using the same procedure, the net power output of the plant for a mass flow rate of 15 kilogram per second. So this is your reading assignment you have to do by yourself after the class or anytime when you are free. Okay, so this you have to read it by yourself. Okay, so now coming towards another important topic, because the main objective of this course is to increase the efficiency of your thermodynamic cycle. Okay, so all the effort which we are doing right now to find the enthalpies to in order to do the actual vapor power cycle to convert into the ideal one. Okay, so this is all happening because we have to we need the maximum efficiency or maximum work output, okay, from our turbine. So we will see that how we can achieve the maximum work from your turbine and how we can increase the efficiency by different ways. So as we already know, when we are talking about the TS diagram, the work for your cycle is this area under the curve. Okay, so the area which I am highlighting right now is the area under this curve is your work cycle. Okay, so in order to increase the work output for your cycle, okay, so W cycle, what we need to do is we need to increase this area. Okay, so how we can increase this area? So if we can notice that if this point 2 or this point 3, we just shift this point to the lower side. Okay, so in this way we just get the this area and added one. Okay, so this mean this W added, okay, which is your added area, increase your work done by work for your cycle. Okay, so this is the one approach that either we can decrease the pressure of your condenser, you can easily get the maximum work for your cycle. Then second approach, okay, so second approach is that either we can just shift this point one to this area. Okay, so this again you can easily get the some added part. Okay, so this is again another approach. Okay, so we will see in detail that how these approaches will work. Okay, so first one is that the idea behind all the modification to increase the thermal efficiency of the power cycle is the same: to increase the average temperature at which heat is transferred to the working fluid in the boiler, or decrease the average temperature at which heat is rejected to the working fluid to the condenser one. Okay, so now the first approach, lowering the condenser pressure, which we already discussed, that we need to increase the area under the curve. Okay, so previously, if this is your W cycle, okay, so now we just have to add it by just lowering this zero point 0.4 to 4 dash. Okay, so once we decrease this pressure, which is your condenser pressure, okay, we get this added area. Okay, so to take the advantage of the increased efficiency at lower pressure, the condenser of the steam power plant usually operate well below the atmospheric pressure. There is a lower limit to this pressure depending on the temperature of the cooling medium. But one side effect for this one, because at the same time we are getting maximum power works for your cycle, but the side effect is that lowering the condenser pressure increases the moisture content. Okay, and which is not desirable for our turbine as well, because once the moisture content is increased in the exit of the turbine, it's mean that your erosion and corrosion will be maximum. Okay, and we do not need that our turbine lifespan will be affected by just increasing the moisture content. So this is not a desirable thing. So we will see that another way. Okay, so the next way is superheating the steam to high temperature. Okay, so first we will see that what is the meant by superheating of the steam. Okay, so superheating mean that previously this is your superheated region. Okay, previously the superheating is on 0.3. Now we just shift to 3 dash. It's mean we are superheating the steam at higher pressure, higher temperature. Okay, so the again now this will be the added area, and this is your W cycle previous one, and this is your W added. Okay, so it's mean that your cycle efficiency will be increased. Okay, because we have to add this up. Okay, so now coming towards some of the part that both the network and heat put increase as a result of superheating the steam to a higher temperature. So in turn, the overall effect is an increase in thermal efficiency. Okay, since the average temperature at which heat is added increases. So again, there will be something that superheating to higher temperature decreases the moisture content of the steam at the turbine exit, which is desirable. So this is the positive thing about superheating. Okay, another thing is that temperature is limited by the metallurgical consideration, because for example our turbine blade is made up of some sort of metal which do not withstand that superheating temperature. Okay, so that's why we have to consider the metallurgical approach as well. Okay, or presently the highest steam temperature allowed at the turbine inlet is about 620 degrees C. So these are the operating temperature for our turbine which we presently use in our steam power plants. Okay, so now coming towards the third approach, which is your increase in boiler pressure. Okay, so now if we just increase the boiler pressure, and other important thing is that your T average, which is your superheating temperature, we have to keep it same. Okay, so T maximum will be same for a, but in this case when we have to increase the boiler pressure, it's mean your boiling point of your working fluid is also increased. Okay, so it's mean we need more work input in your we need more q in your boiler as well. Okay, so in this way what we have to do is we get this added area by just increasing the boiler pressure, but at the same time this 0.3 which is previously at your right side now shifted towards your left one. Okay, so which is 3 dash. So this mean now here we see the decrease in W net, but maybe possible this decrease is small as comparison to this increase, so we still get the maximum efficiency out of it. Okay, so this is another approach in order to get the maximum efficiency or maximum power from your cycle as well. Okay, so now coming towards another thing that today that many plants, steam power plants, operate at supercritical pressure. So supercritical pressure mean this is your critical point. Okay, so today which the operating of your vapor power cycle, we just have to use the supercritical pressure one. So mean that point 3 is above this point. Okay, so that the value of 22.06 megapascal and have thermal efficiency of 40% for fossil fuels and 34% for nuclear plants. Okay, so this is another important information for you. Okay, so now coming towards the question. Okay, so we just apply these approaches. That was three approaches that either we can increase the boiler condenser, decrease the condenser pressure, either we can use the superheating steam, increase the temperature of superheating steam. So how it will affect the thermal efficiency. So just read the question first, that consider a steam power plant operating on the ideal Rankine cycle. Steam entered the turbine at 3 megapascal and 350 degrees Celsius. Okay, 350 degrees Celsius, and it is condensed in the condenser at pressure of 10 kilopascal. So mean that this pressure and this pressure is known to us. Okay, so this is similar to your example 10-1. Okay, so we also have to compare the values of the efficiency from example 10-1, because in this case it is 10 kilopascal. In the, I think, example 10-1, it is 75 kilopascal. So mean that we are lowering the condenser pressure in this case. So we will see that if we compare the efficiency, which is fine by this approach, similar, or maybe it will be higher, or maybe it will be lower. So we will see what is happening. Okay, so determine the thermal efficiency of this power plant. So for case 1, you have to find the thermal efficiency. For the case B, the thermal efficiency if the steam is superheated to 600 degrees Celsius. So in this case, previously we are superheating the steam at 350 degrees Celsius. And now we have to raise the temperature to 600 degrees Celsius. Okay, so third case, the thermal efficiency if the boiler pressure is raised. Okay, so previous two cases, which is A and B, the boiler pressure is 3 megapascal. Now we have to increase the boiler pressure to 15 megapascal. Okay, so this is the third case, and maintaining the inlet temperature of your turbine, inlet temperature is maintained at 600 degrees Celsius. So we will see how your turbine efficiency will look like.
सर
जी,
तो कुछ स्टूडेंट्स कह रहे हैं कि थोड़ा पेस थोड़ी स्लो करें, वो नोट्स वगैरह बना रहे हैं तो साथ उनको मैच नहीं हो पा रही स्पीड उनसे।
जी
अच्छा,
सर,
ठीक ठीक है, मैं कर
काफी
लूँ।
स्पीड है।
ओके, इसलिए मैं जल्दी कर रहा हूँ क्योंकि ये चीज़ें आप पहले पढ़ चुके हैं। ठीक है, ये अभी हमने प्रीवियस क्लास में चेक किया था कि ये एफिशिएंसी इंथैल्पी कैसे फाइंड की है, तो मैंने इसलिए उसको जल्दी जल्दी किया है कि इंथैल्पी वगैरह हम दोबारा नहीं करें। लेकिन चले मैं इसको कोशिश करता हूँ कि थोड़ा सा स्लो करके चलें। Okay, so now we will see that the solution. Okay, so for the state 1, which is your first case. Okay, so for first case, you already know the pressure at your state 1, okay, which is similar to your condenser pressure, which is 10 kilopascal. And we already know that how to find the enthalpy and specific volume for your state number 1. Just go to thermodynamic table and you can easily find the enthalpy value at saturated liquid part and saturated at or specific volume for your saturated liquid case. Okay, so this come from your thermodynamic tables. Okay, so just read it from there. 191 is we already find in the example 10-1 as well. So coming towards state number 2. Okay, so for state number 2, this is 3 megapascal. Okay, for 3 megapascal, this is given in your question that your boiler pressure will be 3 megapascal. As we already know that the entropy for S2 is equal to S1. So we can easily find your pump in from there, which is your specific volume into P2 minus P1. Specific volume come from your state number 1. You already find from thermodynamic table. P2 is given in your question. P1 is also given in your question. Okay, so now you can easily find 3.02 kilojoule per kg. Okay, so now coming towards your enthalpy value at state number 2, H2 is equal to H1 plus pump in. Okay, so pump in you already find from in the previous state. H1 you can find from thermodynamic table. So now all the values given to you, you can easily find the enthalpy value. Okay, so this is already we have done in example 10-1 as well. So again you have to find for state number 3, all the values are given to you in the form of thermodynamics table. You can just read it from there. Okay, so now coming towards or the state number 4, again P4 is the same one, 10 kilopascal. You can find the quality at that point by using this relation which we use in example 10-1 as well. Okay, so this is given to you from your previous state, because S4 is equal to S3, and this SF you can easily read from your thermodynamics table against a 10 kilopascal pressure, and now you can just plug in all the value, you will get the quality as well. So enthalpy for point 4 you can again find from thermodynamics table. This is come from thermodynamic table. This you already find in the previous case, which is X4, this one. Okay, and this also you can find from thermodynamics table. Once all the value is known to you, you can easily find Q in and Q out. Okay. So just you need H3 minus H2, you can easily find Q in and Q out, H4 minus H1, which come from your energy and balance equation, which we already discussed in the previous lecture as well. Okay, so now the main point is that what is the effect on thermal efficiency, because we already know that the thermal efficiency is Q out over Q in. Okay, so now you can easily find Q out from this relation and Q in from this relation. Okay, so now the thermal efficiency become 33.4%. So therefore, if we just compare from example 10-1, so in example 10.1, the thermal efficiency is 26.0%. Okay, for your condenser pressure P4 is equal to 75 kilopascal case. Now your thermal efficiency become 33.4%. So therefore you can easily see there will be an increase in thermal efficiency by just lowering the condenser pressure. Okay, so which we already discussed that if we decrease the condenser pressure, it's mean your area under the curve will be increased. Okay, and once that area under the curve increase, it's turn out to be increase in thermal efficiency, and your cycle work is also increased. Okay, so at the same time, by just decreasing the pressure at your condenser, the quality of the steam decreases from 88.6 to 81.3%. So what does this mean? It's mean that the moisture content increased from 11.4 to 18.7%. Okay, so that is not desirable for us, that we do not want that the moisture content will be increased. Okay, so this is a negative thing for decreasing the pressure in the condenser, and we have to avoid it. Okay, so coming towards the second part. Okay, so in the second part, what we have to do is, previously the superheating temperature, which is your T3, is 350 degrees Celsius. Okay, and now we just increase the T3 to 600 degrees Celsius for your case B. Okay, so now we will see that what is the effect. So again, the approach is the same. You have to find the enthalpy value at H3, H4, because H1 and H2 is similar to your previous case. So you already find the enthalpy value of H1 and H2 in the A part. So Q in you have to find out, Q out you have to find out. Okay, and then plug in all the value and you will get the thermal efficiency of 37.3%. Okay, so now just compare with the previous thermal efficiency. So previously you get 33.4 in the part A, now you get 37.3 in the part B. Okay, so now if we just compare, we will again see there will be an increase in thermal efficiency, but that increase is not so much high. But again, the issue is that at the same time, the quality of the steam increases from 81.3 to 91.5%. In other words, the moisture content decreases, and decrease in moisture content is desirable for turbine as well, because we get the minimum erosion and corrosion effect. So that is desirable while designing the turbines as well. So this is the difference between increasing the superheating temperature. So now coming towards your point 3, which is C part. So in the C part, what we have done, we just have to increase your boiler pressure, which is 15 megapascal. Okay, so 15 megapascal, once previously it is operating on 3 megapascal. So now we increase to 15 megapascal. So again, you have to find all the enthalpies value H2, H3, H4 by using the same approach we already found from the ideal Rankine cycle. So just plug in all the value Q in and Q out, and now you have to plug in this equation, and you will get 43%. So now we will just compare from your case number B. So in the case B, it is 37.3%. Okay, and in this case, it is 43%. So there will be a increase in thermal efficiency by just increasing your superheated temperature. Okay, so by just increasing superheated temperature to 600 degrees Celsius. This one is which is increasing your pressure in the boiler one. So P3 we just increase from 15 megapascal from 3 megapascal, which is in your case B. So we will get the increase in thermal efficiency. So again in this case, at the same time, the quality of the steam decreases from 91.5 to 80.4%. So if we find the quality, we can easily compare with the previous cases. Okay. In the other word, the moisture content increases from 8.5 to 19.6%. So this is again the moisture content is increased. So this is not desirable for your turbine as well, because we do not want the turbine lifespan is less due to the erosion and corrosion. So this is how we can see fluctuation in the thermal efficiency by just playing with the two parameters: superheated temperature, your boiler pressure, and your condenser pressure. Okay, so any question till this point?
No, sir.
Okay, so I hope this will be a very easy one, but I will suggest that you have to practice all the question which I already see. Just go through in these slides by yourself, because in this case, whenever we are going for the sessional exam, you will not see the problems that are easy like this. Okay, so you will have a good knowledge about how to find the enthalpy and how to find different pressure, temperature at different states. Okay. So that's why I will suggest you have to practice all the question by yourself after the class as well. Okay, so now we will go for 10-minute breaks. Okay, and after the break, we will start with the another topic, which is your reheat cycle. Okay, so if you have any question, you can ask me, or we will go for 10-minute break, and then we will come and start the session again. Okay, so we will start again, okay, with the new topic. Okay, so in just we already looked at by increasing the boiler pressure, okay, boiler pressure in your this area, this will increase the your thermal efficiency as comparison to all the other cases, which we already see in example 10-3. Okay, so but at the same time, one drawback for this is that by increasing the boiler pressure, you will get you already you can anybody confirm that you hear my voice or
Yes, sir, you're audible.
okay. Okay, so we do not want that this decrease will be happen. Okay, so in previously that your the third case is producing maximum efficiency. So how to deal with this situation that we don't, if we do not want that this decrease will happen, instead of this will also be useful for increasing the efficiency. So we use the reheating of the steam. Okay, so what is the reheating of the steam? We will see that how reheating will work. Okay, so for the reheating one, what we have to do is we have to okay, so this is also similar to your Rankine cycle. Again, the boiler is the same, pump is there, condenser is there. But instead of using one turbine, which is in your previous case, we are using now one and two turbine. One is low pressure turbine and one is and another one is high pressure turbine. So what is the use of this one? Previously, we are using one heat addition process. In this case, we are using two heat addition process in the boiler. So as you see that in the between 2 to 3, there will be a heat addition, okay, which is your to raise the temperature to the superheating region. Okay, so again by using 4 to 5, again we are superheating the steam. So as the steam which come from to state number 4, okay, it got decrease in temperature, so again we want to add some heat and again we turn it into the superheated one by raising the temperature. So in this way, by just adding another turbine, which is your low pressure and high pressure turbine, we get increase the area as well. Okay, so previously, which is the decrease one, now it's also contributing adding the this area under the curve. Okay, so this means that W cycle will increase and your efficiency of this cycle will also increase. So now we will see that how to, okay, so before this, another important thing is that we can take advantage of increase in efficiency at higher boiler pressure without facing the problem. Okay, so superheat the steam to a very high temperature. Again, there will be a metallurgical issues for this because mostly we are using steel or something like this, and possible that the high temperature is not withstandable for this material. So that will be another issue. Another important thing is that expand the steam in the turbine two stages. So we need to find Q in most of the cases for doing the thermodynamic analysis for this reheating vapor power cycle. So now we already know that there will be a two heat addition process in this. So Q primary and Q reheat. Okay, so Q primary, which is already seen in your previous one, which we already see in the previous cases, and reheat, which we have added in this reheat cycle. So again, doing the energy analysis, H3 minus H2, this is your exit one, this is your inlet one, again H5 minus H4. Okay, so you just have to add all this Q primary and Q reheat to get the total heat input. Now again turbine out. So in this case there will be a two turbine. So definitely we have to add both of the work for the turbine 1 and turbine 2. So again by using this relation you can just add up all the enthalpies for this one and you get the turbine out. So now looking towards some advantage and disadvantage of our reheating process. Okay, so one thing that is important is that the single reheat in the modern power plants improve the cycle efficiency by 4 to 5% by increasing the average temperature at which heat is transferred to the steam. So it's mean that 4 to 5% of your efficiency is increased by just adding one reheat cycle, one reheat process. Okay, so the average temperature during the reheat process can be increased by increasing the number of expansion and reheat stages. So as we increase the number of reheat stages, it's mean that your average temperature is increased. So in turn, it will increase the efficiency of your turbine, efficiency of the whole stage as well. Okay, so then another important thing, the use of more than two reheat stages is not practical. Okay, so why this is not practical? Because whenever you have to use more than two reheat stages, it means that your maintenance cost will be high because you have to add more turbines, okay, in your vapor power cycle. So that is not a practical one because the cost is one of the most important issue while designing the vapor power cycle. Okay, so another thing is, okay, so these are to just, okay, so advantage and disadvantage of your reheating. So there is an increase in output of the turbine, which is a good thing. Erosion and corrosion problem in the turbine are eliminated and avoided because your moisture content is decreased in this case. Because once we have to reheat, the moisture content will decrease. So this is a desirable thing for your turbine as well. So there is an improvement in the thermal efficiency of the turbine, which is a good thing because we want our thermal efficiency will be higher. Final dryness fraction of the steam is improved, and there is an increase in nozzle and blade efficiency as well by just adding the reheating in the turbine in your vapor power cycle. So then there will be a disadvantage advantages which we are reheating require more maintenance, which we already discussed that by just adding the more turbine, it's mean that your maintenance cost will be higher, and we do not want that our maintenance cost will be higher. Okay, so increase in thermal efficiency is not appreciable in comparison to the expenditure incurred in the reheating. Okay, so that is another important thing that we do not want. The expenditure will be more. Okay, so now just if we can see that if we have to add number of reheat stages, okay, so the average temperature at which heat is transferred during the reheating increases as the number of reheat stages is increased. Okay, so this is just an information for you. Okay, so now we will just see the example. In this way, you will get better understand what is the reheating process and how to thermodynamically analyze the reheating uh, vapor power cycle. Okay, another important thing is after this question you have to do one question by yourself, so you have to just listen it carefully that how to perform all the thermodynamically approach so that we can find the enthalpy value at all the states. Okay, so to find the thermal efficiency of the this cycle. So you have to do one question after this. So first read the question. So consider a steam power plant operating on the ideal reheat Rankine cycle. So it's mean that this is the ideal case, but it will be a reheat Rankine cycle. Steam enter the high pressure turbine. So there will be a two turbines. So high pressure turbine is between 3 and 4. Okay, so it's mean that the pressure at your 3, 15 megapascal and 600 degrees Celsius. And is condensed in the condenser at the pressure of 10 kilopascal. Okay, so it's mean that your condenser pressure is also given to you in the question. So if the moisture content in the steam at the exit of the low pressure turbine, it means that point number 6, the moisture content is given that is not exceed to 10.4%. So determine the pressure at which steam should be reheated. So it's mean that we have to find P4 and P5, which is we have to find from this data. The thermal efficiency of the cycle we have to find out by just finding out all the values of enthalpies at all the states. Okay, so another thing is assume the steam is reheated to inlet temperature of the high pressure turbine. Okay, so this is an again information we will use in the solving this question. So now coming towards the question. Okay, so as we know that the pressure at the condenser is given to us in the question, so we have to find the enthalpies value at all the state. So you have to start from stage number 6. So previously we start from state number 1. So it is it depends on the question and the data available. So where we have to start, because at P6 if we start we can easily find the enthalpies value for the rest of the stages. So P6 the pressure is given. Okay, so this is given in your question. The moisture content at the exit of your turbine, that is low pressure turbine. Okay, so S6 you can find from thermodynamics table. SF is your saturated liquid entropy value. This is given in your question. This also you can find the thermodynamic from thermodynamic table. So just plug in all the value, you will get the value of entropy value at point number 6 as well. So again we have to find the enthalpy value also. So for enthalpy value, again using the same thermodynamics table, and for the pressure one, 10 kilopascal. So you can get all the value from thermodynamic table, and you can just plug in all the value and you will easily get the enthalpy value at state number 6 as well. So now question is that how to find the enthalpy pressure value at state number 5. Okay, because we have to find the pressure value at number 5. So as we already know that it is given in the question that T5 is equal to 600 degrees Celsius. Okay, and then S5 is equal to S6 because it is an isentropic process. So from this data we can easily find P5. As you already know that the T5 is in superheated region. So now we have to go to superheated region. Okay, so superheated region over is your okay. So in this case, to find the pressure, we have to use trial and error method. Okay, so what is the trial and error method? We have to just note down the entropy value at state number 5. Okay, so which is 7.3688. Okay, so if we just have to find out the value from of the pressure, we just have to keep look on 600 degrees Celsius, which is mentioned in your uh, question as well. Okay, and then we have to look the entropy value because S5 is equal to S6. So you have to look all the table. Okay, so here if you can notice 600, there's the value is 10.16. Okay, so which means it is very far from our S5 value or S6 value. So we have just look all the table. So whatever the region where you have to find the value which is closer to you, this 7.3688, you just have to stop at that point. For example, at 2.5 megapascal, the 600, it is 7.59 79. So it's mean still it is higher. Okay, so you have to just bring down to 4 megapascal, and for the 4 megapascal, if you just noted at 600 degrees Celsius, you will get 7.3706. Okay, so this value is closer to the value which is your 7.3688. Okay, so this value will be closer at 4 megapascal. So you just have to go through all the table. Okay, and just compare your enthalpy entropy value, and whatever the pressure range in which your entropy value is closer to this value, you can just note it down that this is your pressure at number 5. So this is the trial and error process. So you have to just spend some time to finding out the P5 range. Okay, so again you have to find the enthalpy value at state number 5 as well. So just again you have to follow the same table. So for example, at P4 600 degrees Celsius, you just have to note down the enthalpy value, which is 3674.9 at your superheated region. So you can see easily that the enthalpy value is given to you by using the thermodynamics table 3674.9. So this is how we can find the properties at number state 5. Okay, so now coming towards your point B, to find the thermal efficiency, and you already know that in order to find the thermal efficiency you have to find all the enthalpies value. So we will start from state number 1. We already know that 10 kilopascal is given that condenser pressure, and P6 is equal to P1. H1 and specific volume 1 you can easily find from your thermodynamics table. Okay, that would be not an issue. So P2 is again given that P2 is equal to P3. P3 is given in the question, and P2 is known. S2 is equal to S1, which we already find from previous state. So you can find your work supplied to your pump to specific volume P2 minus P1. Specific volume is given to you. This is given in the question. This is given in the question, and you can find the pump work. And same for the enthalpy also, H1 plus W pump in, you can easily find the enthalpy value also. Okay, so now coming toward next point, which is state number 3. Okay, so state number 3, your temperature and pressure for the steam is given. Okay, so it's mean it will be a superheated region. You can easily go to superheated water table and find the enthalpy's value at this stage as well. Okay, so now the issue will be with the state number 4. Okay, because at the state number 4, the pressure is given and enthalpy is given. Okay, rest of the thing we do not know that how to find this value. So we already know that S4 is equal to S3. So how to find this H4 and T4? Because this is not a simple like the previous cases. Just read from the table and you can easily mark it that this is H4 and this is T4. So what you have to do is you have to bring some mathematic knowledge. Okay, so which is your linear interpolation. You already know the linear interpolation, that what is the meaning of linear interpolation. So it's mean that, for example, if there is a 3 points, for example, this is 1, this is 2, this is 3. Okay, and you have to find some value at state number 2, and all the values at state number 1 and 3 is given to you. So you can easily find by using the interpolation. For example, in this case, the x naught and y naught is given at state number 1. At state number 2, x is mentioned or y you have to find out. Okay, or state number 3, x1 is mentioned or y1 is also mentioned. So you can just plug in all the value in this equation. So this comes from linear interpolation. If you do not know how to do the linear interpolation, you can go and just revise your mathematics. Okay, I think you already have been taught in the previous course that how to do linear interpolation. So what we have to do is just you have to go to thermodynamic table. Okay, because we already know that this is that state number 4 is the superheated one. Okay, so superheated one, so we have to go to superheated table, and we know that T4 is your 4 megapascal. Okay, so what we have to do is you just have to, okay, so from the previous knowledge we also that our S4 is equal to 6.6796. So you have to note it down that this value, because we have to use this value, S4 value 6.6796. So 6.6796. So you have to look down that between this region 6.5843 and 6.7714 mean that between these two value the 6.6796 value exit. Okay, once you know that the value is in between these 2 points, so you got some understanding about it, that you have to apply linear interpolation between 350 and 400 range. Okay, in order to find the enthalpy value and temperature value in between this range. Okay, so now you just have to note down all the value, because your temperature at state number 1, which is your 350 degrees Celsius, which come from your thermodynamic table. Okay, so you just have to, so this come from your thermodynamic table. Okay, for your superheated one, this temperature you have to find out. Okay, this again come from your thermodynamic table. Entropy value you just have to read, which is in line with 350 Celsius. So this 6.6796 come from your, because S4 is equal to S5. Okay, so you just have to see that S4 is equal to S3. Okay, so this come from, okay, so this come from S4 is equal to S3, and this come from against the 400 degrees C temperature. Again, you have to note down all the enthalpy value also against 350, 3093. It is mentioned in your thermodynamic table, and enthalpy at state number again you have to find at state number 4. Okay, and then 3214.5. This is come against your 400 degrees Celsius. So once all these values are known to you, you can just plug in this equation, and you can easily find the temperature value and enthalpy value. So we will see that. I will just go quickly and do some calculation to find out the values for your temperature first. Okay, so first we have to find the temperature. Okay, for state number 4. Okay, so temperature is minus 350. Okay, so your y is in between. Y naught mean your 350 temperature 6.6796. Okay, so this is your linear interpolation method. Okay, so this has come from your mathematical knowledge. 6.5843, which is equal to y1 minus y naught. So what is y1 in this? Y1 is 400, y naught is 350. Okay, so this is 400 and this is 350 divided by your x1 minus x naught. So x1 is 6.7714 minus 6.5843. So you can just solve for t and you will get the value of t is equal to 375.46. Okay, so if you can just okay, so you can just notice that by just doing the linear interpolation, you can find this value T4, which is equal to 375.5 degrees Celsius. So in this way, you can find the value at state number 4. So again, you have to apply the interpolation to find the enthalpy value also. So in this case, you have to apply the linear interpolation 2 times. Okay, so now we will see how we can apply the linear interpolation to find the enthalpy value. So again, okay, so now you will already find this value. So this is 375.46. Okay, so you already calculated. So now you have to use this value also in order to find the enthalpy value. Okay, so now again you have to apply the linear interpolation. So now previously this is not known to us. Now we have already find out, and 375.46, or you can say 5 minus 350 x minus x naught. Okay, previously we are using entropy value. Now we have to find the enthalpy value. So we have to just apply the enthalpy value over there. Okay, so H2 is unknown to us. We have to find it. X naught 3093.3. Okay, so this come from here is equal to y1. What is the y1? 400 minus 350 divided by 3214, which is your x1, 0.5. Okay, so this is your x1 minus 3093.3. Okay, so this is come from there. So if you just have to solve for h2 by using your calculators, okay, so you will get the value h2 is equal to 3154.71. Okay, so now we will see that in the previous slide. Okay, so as you see that h4 is 3155.0. Okay, so this is how you can find the h4 and t4 by using linear interpolation. Okay, so you already have to revise it. Okay, so you can just go and revise your mathematics knowledge. So how to apply linear interpolation for 3 points. Okay, so now coming towards our main thing, that we have to find the thermal efficiency for the reheat cycle. So we need Q in for this. So Q in, we already know that there will be two heat addition process. One is between 3 and 2. Okay, so there will be a heat addition, and one is between 5 and 4. Okay, so we need enthalpy value at state number 3, enthalpy value at state number 2, enthalpy value at state number 5, enthalpy at state number 4. So which is your Q in value. So just plug in all the value, because you already find all the values in previous states. You can get the Q in. So again for Q out, so for Q out it is in condenser 1. So this is your Q out. So Q H6 minus H1. So you can just plug in H6 value and H1 value. So you can find the value of Q out as well. To find the thermal efficiency, you just need the 1 minus Q out over Q in, and you can find the thermal efficiency of your whole reheat cycle in this way. Okay, so this is the approach we have to use in order to find the enthalpy value and to find the thermal efficiency for the reheat Rankine cycle. Okay, so any question till this point? Okay, so I hope there will be no question, and it is an easy one also. Okay, so what you have to do is you just have to note down this question and first read the statement, because this you have to do it by yourself. Okay, so steam power plant operates on the ideal reheat Rankine cycle. Okay, steam enters the high pressure turbine at 8 megapascal and 500 degrees Celsius. So again, the pressure at 3 is given to you, leaves at 3 megapascal. Okay, so one thing which is different from the previous one, previously you have to find this P4 or P5. So now P4 and P5 is given in the question as well. So steam is then reheated at constant pressure to 500 degrees C before it expands to 20 kilopascal. It means that this pressure is also given to you. Okay, and temperature is also mentioned. Low pressure determine the turbine work output. Okay, and the thermal efficiency of the cycle, and also show on the cycle on TS diagram. So this one is also an easy one. So all the states points are given to you. The information that is P4 and temperature is given to you. You have to find helpers value at all the state and plug in all the value in the efficiency equation. You can find the thermal efficiency of the cycle. So just note this question, and you just have to reply me within 15 minutes. So I will give you 15 minutes. You have to mention your ID, you have to mention your section, and you have to mention the value of thermal efficiency and your turbine work by turbine. Okay, and again, another important thing is, do not have to reply on me on the thermodynamic channel. Okay, so you have to go to inbox and just write all the information there and just send me an inbox. Okay, rather than just you have to reply me on the channel which we have built for this class. Okay, so do not do this, do this. Okay, so if you have any question you can ask me, or I will give you 2 minutes to note down this question.
रिप्लाई टीम्स चैनल पे आपको डीएम में करना है ना?
जी, आपने उसी पे मुझे जो है ना वो इनबॉक्स करना है। आपने चैनल के अंदर मुझे रिप्लाई नहीं करना, क्योंकि चैनल में रिप्लाई
जो आईडी है उस पे आपको रिप्लाई करना है।
जी, उस पे रिप्लाई कर दें, लेकिन आपने चैनल जो थर्मोडायनेमिक्स का हमारा बना हुआ है ना चैनल, जिस पे आपकी क्लास हो रही है, उस पे आपने रिप्लाई नहीं करना, क्योंकि उससे ये होता है कि सबको मैसेज चला जाता है।
ओके।
Okay, so I hope there will be no question. Okay, so I'm leaving now. If you have any question, you can also inbox me and ask me anything. Okay, after the class as well. And I'm just going to stop this meeting right now, and first I will stop the recording.